Good morning, everyone. Mr. Zatola here with the next note sheet. This is Notes 19, Intro to Meteorology. so let's get right into it. Meteorology is the study of weather, and really what we mean is the study of what's going on in our atmosphere right now. When we talk about weather, we're talking about the current weather. We're not talking about a long time period. We're talking about this second. So let's get started, okay? This first chart we're going to take a look at is page 14 of your Earth Science Reference Tables. It is the Earth's atmospheric layers and some characteristics for each. So let's start at the bottom right here. So we are in the troposphere. That's at the surface. Here's sea level. That's the surface of the Earth. All weather takes place in the troposphere. And that has a lot to do with the fact that most of the water vapor available for any type of heat transfer is at the surface. So the majority of it is down in here, okay? So water plays a big role in weather. Water has a high specific heat. It takes time for it to warm up, and it takes time for it to cool down. It holds on to heat very well. It does not transfer heat very well, so it influences a lot of our weather, okay? Density has a lot to do with weather as well, and we'll get into that a little bit further down the road, but let's take a look at some characteristics here. So again, water is what we see the most of. We see the most water in the troposphere, okay? We move over. The next part is the stratosphere. We pass through the stratopause. We go to the mesosphere. We pass through the mesopause and the thermosphere. The pauses just have to do with where one piece of the atmosphere ends, another begins. These are not hard set locations. This is an average of heights for each one. So don't feel like you have to memorize. These actually change over time, and they change because they are based on temperature. So let's take a look at the next piece in this chart. So temperature is right here. We notice at surface, we start about 15 degrees Celsius. And as we get higher in elevation, as we increase elevation, the temperature decreases. Okay, it goes to about negative 55. And then we see it start to increase back up. And this happens somewhere around, 6 to 8 miles above the surface and about 12 kilometers. Okay, that's where the temperature starts to increase. But remember, when I say increase, I'm not talking increase a lot. It increases to 0 now. All right, so the atmosphere is still pretty darn cold there. So we've gotten very cold, negative 55, and now we're headed back up as we pass through the stratosphere. Once we exit the stratosphere, we're starting to head back past the stratopause, and sure enough, temperature decreases again in the mesosphere, and sure enough, it decreases to about negative 90. It's really cold up there, and that goes to about 50 miles or 80 kilometers above the Earth's surface. And then we start to gradually increase temperature, but this is kind of a false right here. There's not a lot in the thermosphere up here. And what I mean by there's not a lot of air particles. There certainly isn't any water particles, so there's nothing to hold heat there. But there's also not a lot of gases that high because, well, the atmosphere kind of phases out up here. It's very grainy. It sort of floats away. There's nothing there. And also gravity. Gravity holds everything down close to the ground that has weight, and all the molecules you might be thinking of have weight. And that's why we see this piece of pressure. I'm just going to take a look. Pressure, just right here, most of the pressure exists at the Earth's surface. Matter of fact, 1 atmosphere is at the Earth's surface. Pressure decreases rapidly and really almost goes to nothing before you exit the stratosphere. This is why airplanes that fly in the stratosphere have to be pressurized because there is no pressure. There is no air. There's nothing up there. If you've ever watched the movie Everest, you know that most of the time, there are occasions when people didn't. If you don't keep your oxygen mask on, you're going to die, okay? And that's part of why the thermosphere, although it does not get super duper warm. This, I wouldn't go by that at all. It does definitely warm up, but only when you're up there, and that's because your proximity to the sun. All right, so big piece here. All of the weather on the Earth occurs in the troposphere. It's because of where all the water vapor is. Okay. The next chart we're going to look at is on page 1 of your Earth Science reference tables. This is a chart that broke down the crust, the hydrosphere, and finally we're going to talk about the troposphere, what elements we find there. Something that's really interesting and students always get caught on, the most abundant element in our atmosphere is nitrogen, 78%, okay? Not oxygen. Oxygen is only 21%. And then there's some others. We have CO2, we have H2O, there's methane, there's particulate, and that's 1%, and that's what we call other all the way down there. There's greenhouse gases and whatnot, and we'll get into that a little further. So again, this is page 1 of your reference tables where you'll find percent by volume, elements in the troposphere. Okay. So weather is the current state of the atmosphere. We determine it by looking at a lot of factors, okay? Temperature is a big one. Air pressure is a big one. Humidity is a huge one. And then we'll talk about wind that can affect all three of those. And really, they're affected. They make wind in some cases. Pressure is a big piece of that. Temperature is a big piece of that as well. All right, all of these factors down here influence each other. Okay, the amount of humidity, the amount of temperature, and the amount of pressure all factor in to each other. And that's what we get for weather. So how do we determine these pieces? Well, we use weather instruments, and you do need to know these for the notes, and we'll take a look. So you probably remember some of them. You know that a thermometer measures temperature. Okay, it measures temperature in degrees. Okay, if you're really savvy and you love a little knowledge, we know it's in Fahrenheit, degrees Fahrenheit, or degrees Celsius. If you're looking on your reference tables at the temperature chart, you're going to notice there's something called Kelvin as well. Yeah, we don't use Kelvin much in earth science. Kelvin is a way of determining temperature at a very, very cold, where it's looking for absolute zero. That's when there's absolutely no molecule movement, but we've not reached it yet. So the elusive Kelvin. All right, we move on to something where we measure pressure, and we use a barometer or a barometer. All right, that's air pressure. And air pressure can be measured in millibars, or in this case, we have inches of mercury. And you're going to also see that if you look on page 13 at the pressure conversion chart, we're going to look at that down the road. That it's got two sides to it, millibars and inches of mercury. We spend most of our time in millibars, but you should know that there's other options. Okay. We measure humidity using two items. One's a hygrometer and one's a sling psychrometer. There's a really good chance you might have seen someone spinning a sling psychrometer around. That's what it is. The hygrometer measures two types of temperature, a wet bulb temperature and a dry bulb temperature. And we're going to look into that when we discuss humidity further. We measure that in percent. So you probably remember on the weatherman, he's saying 100% humidity or 0% humidity. That's exactly what they're doing there. All right. The next instrument we're going to talk about is the anemometer. Maybe you've seen one. This measures wind speed. All right, it looks like a little propeller sitting on a stalk, and what happens is it spins just like something, a little propeller like that, and it spins and tells us how fast the wind is going. It tells us how fast the wind is going using miles per hour, traditional, and something called knots. These are not nautical knots if you are into sailing. These are a different version of knots. They're wind speed knots. Airplanes use these type of knots. Not too far off, only a few miles per hour per knot. Along with wind speed, we also have to know a real big thing, wind direction. And maybe you see this, a weather vane, all right? Some people call it like the chicken or the rooster on top of the farmhouse. We got some farms around here, right? It's got a little north, south, east, and west. All right, and maybe there's something on top that spins, and it tells us the direction wind is coming from. And that's important because wind We talk about wind, we talk about where it's coming from, because wind coming from the north generally is colder than wind coming from the south. Generally, I don't want to say all the time, but start remembering that wind is noted and called from where it comes from, and that's what a weather vane tells us. All right. The next thing we're going to check is precipitation. This is pretty interesting. So we use a rain gauge for precipitation. We measure in inches, and it is like a large cup or a large column. It is just an open container that fills with water. Okay. And lastly, we're going to use our eyes, yes, to determine cloud cover, and we're going to call that in percent. So it's 100% cloudy or overcast is also how we call 100% cloudy, or it could be no percent cloudy or 50% cloudy or whatever, something simple. Great. So let's get a little more in depth. Temperature. Okay. Temperature is the average kinetic energy of the molecules or particles, material that's in the air. In this case, we're talking about the gases. Each molecule moves. The higher or faster it moves, the higher kinetic energy it has, the higher the temperature. Okay? And the slower it moves, the slower the kinetic energy, and the lower the temperature. This map right here is what we call an isotherm map. Okay? This is lines that connect points of equal temperature. Similar to a contour line map that we did, but the isotherm map does temperatures. Okay? And maybe you've seen one of these on TV, on your weather station. It's real simple. There are some factors that we can determine looking at where they're close together or where they're further apart. We'll leave that for next piece. You will see some isotherm maps coming up in some videos. Something to remember is there's temperature gradient, just like there's a gradient in on contours. The higher the gradient, in this case, the higher the gradient, or the lower the gradient, is based on how close the lines are spaced together. Right? So when the lines are spaced together very close, all right, we have a high gradient. That's a large change in temperature over a distance. And then when the lines are not very close, we have a very little bit change in temperature over a distance. Okay? It's important to know that because it's going to affect wind and how weather presents itself to us. Great. So, temperature. Okay, temperature is all about density, or really density is all about temperature, okay? As the temperature increases, the density decreases. They're inverse. So a higher temperature has a lower density, and a lower temperature has a higher density, okay? So hot things have low density and they will rise, okay? Cold things have a higher density and they will sink, right? What happens is this causes a movement of air or a cycle, all right? The movement of air is due to the differences in density. This causes convection, and this is what causes wind. Differences in density and heating and cooling cause wind. All right? When you have these movements of temperature, it changes the air pressure. All right? This is air pressure is easily thought of as the weight of something over you. You probably know this by going into a pool and feeling the weight of water above your head. Maybe your ears hurt, okay? We can do this with air as well, and really the molecules in our atmosphere. When you're at the Earth's surface, you are getting about 14.7 pounds per square inch, and you don't feel this. It's because your body is used to it. It has equalized the pressure. Maybe when you go over the mountains to drive towards West Point or something, you feel your ears pop. That is your body attempting to equalize the pressure. As you're climbing those mountains, air pressure is decreasing. Maybe you know this from going up in a plane. As you increase your elevation or altitude, you're decreasing the pressure, and therefore you must equalize it with your body, or it can hurt. Right? Pressure is the same as density of air, okay? The higher the pressure, right, the higher the density. The lower the pressure, the lower the density. Generally, the lower the pressure, the lower the density, the warmer it is, And the higher the pressure, the higher the density, the cooler air is. Okay, so sure enough, we have a low pressure high up in the mountains, and we have a high pressure low down in the valley. Okay, we could use this little phrase as air pressure decreases with an increase in altitude. Right, so the further up you go, the lower the pressure gets. And then if you come all the way down to the bottom, the higher the pressure gets. You might not really notice this that much, but it does, okay? It happens. And a lot of things we don't notice because we're so used to them and our body's so able to handle that. In this model, we're just showing if you were standing here at the bottom, just showing how every 10 miles decreases pressure by a factor of 10. All right, you don't have to be specific on it, but it is nice to know that wherever you go, there is this column of air above your head. And that is what's affecting pressure in your body and how you feel it. The higher you go, the lower the pressure. The closer to the center of the earth, the higher the pressure. So this slides a lot. How do we measure pressure? We measure pressure with a barometer. Okay, this is a mercury barometer. We don't use these anymore because mercury is, well, it's deadly. It's a poison to us humans. So this barometer, okay, what happens is the atmosphere exerts a pressure on it, and that causes this interior liquid to rise. And we can measure that, okay? It's not important to get too far into it, but we used to own one. I like to say this at the school, and there was a bit of a spill, and that is now gone, all right? You don't want to be around liquid mercury. It just absorbs into your skin. It's kind of creepy and deadly. Okay. So here is a pressure chart, okay? We have a low pressure here. We have a high pressure here. Pressure, all right, or isobars, all right, are measured connecting points of equal pressure. So everything on this line has the same pressure, okay? And I've drawn the L for low pressure in here, and I've drawn the H for high pressure up here. I know it's there. I know it's going to come up, but you should also be aware of it. We're going to take a look. I was able to do that real fast because I know the PowerPoint, but I'm also looking at the wind circulation and how the isobars are placed. So this is a low pressure center. Here's a high pressure center. All right, we're going to talk further about the weather associated with low pressure centers and what these little flaggy things mean, what's going on with them. All right. Barometric pressure maps are probably the most used item for determining weather, although you probably don't see many of them on the weather report. Those you usually use a temperature map, and you'll see little H's and L's moving around. So pressure influences wind. All right, wind is the horizontal movement of air. It's named for where it comes from. We just mentioned that earlier, and it's caused by a difference in air pressure. This is important. Winds move from high pressure to low pressure. So if I go back to my map here, and I'm telling you this is high pressure up here, I'm telling you there's low pressure here, wind is moving this direction generally from the high to the low. All right, we can calculate the difference in pressure and how much wind we're getting by doing a pressure gradient. Same thing as doing a gradient equation, but now we're just going to use pressure numbers. So what does that tell us? Well, the closer the isobars are, the higher the pressure gradient. So the closer they are, the faster wind moves. And the further apart they are, the slower wind moves. Back to our map. And sure enough, what do I see here? Well, I see some areas where we have high winds and some areas where you have almost no wind, or really no wind at all. And this is the map with that. And sure enough, we're going to see high wind speeds. And this is one of our highest using these little flaggy things. It's telling us that. And low wind speeds, there's no flaggy things on those here. And that tells me there's no wind happening. Okay, we're going to talk about how to read those in a little bit. Next thing is sea breeze and land breeze. These are really interesting. They are named for where the wind is coming from. So a sea breeze, the wind is coming from the sea. Okay, so this has a lot to do with the differences in how the world heats. The sand and soil and dirt tends to heat very fast. It's got a low specific heat. The water out here has a high specific heat and it heats very slow. So during the day, all right, here's Mr. Sun, all right, the land heats up, causing air to rise. It's got a low density. We would say the land heats fast, low pressure, okay? The water, all right, try and change my transparency so you can see it. The water over here water heats slow and it causes it to be cooler air above it and a higher density. So what does that mean? Well, ultimately what this means is that this low pressure, low density air is rising, the high pressure, high density air is descending, and it's causing this cycle, convection cycle. And in turn, the wind is coming from the sea in the daytime. Well, what happens at night? So now there's no heating aspect to this. This is the moon, bad moon, but it's a moon. And since the water has a high specific heat, all right, it stays warm. It took all day to warm it up, and now it's staying warm at night. It's warm, so that means the air above it will have a low density and rise. Right? Well, the land, on the other hand, cools fast because it has a low specific heat. All right? So because that cools fast, the air above it is cold and the air will have a high density and descend, and sure enough, we get a cycle like this. And we call air at the surface coming from the land a land breeze. Okay, and that happens at night. It's important to know how that works. If you've ever been to the beach, you'll understand a lot of these concepts. So let's look at a larger scale situation with pressures. Okay, so on a weather map like this, you're going to see pressure centers. Here is a high pressure center. Here is a low pressure center. Okay, how do we know it's a high? Well, look at the wind movement around each one. So at the low pressure, we're going to see winds moving in a counterclockwise fashion, okay, and towards the low pressure, so inward. And at the high pressure, we're going to see winds moving away and outward. Okay, and we're going to have a little bit of a phrase to remember this by, but you do need to understand how wind patterns differ around a low and high pressure. So, high pressures result in cold air descending, dropping. It's cold, so it's dropping. It's higher density. All right. They spiral outward and in a clockwise direction. Great. So, how do I remember this? Well, I do my best to remember that the clock is high on the wall. And sure enough, if I think about it, I have clockwise rotation in a high pressure system. Okay. And we generally have fair or clear skies because of high pressure descending air. Low pressure, on the other hand, all right. So this is air is rising. Okay. This is air moving upwards and in a counterclockwise direction. And how do I remember that? Well, I have another phrase. You could say counter is low in the room. And sure enough, what parts of that do I take away? Well, I take counter and low. So low pressure counterclockwise rotation. And if you remember that winds always move from a high to a low pressure, you'll understand outward from high and inward for low. All right. Lows produce lousy weather. When we have a storm, it's a low pressure system. All right. You might be thinking, well, why does this stuff spin? Well, the spiraling that we see that happens on the Earth is due to Coriolis. Coriolis is the effect that takes place because the Earth is constantly spinning. Right, the Earth rotates on its axis, and therefore causes winds to rotate. It causes lots of things to rotate, ocean currents as well. So let's look at this in a full situation here. So winds blow from a high to a low pressure. So note they're going out and down at a high pressure system. They're coming in and rising at a low pressure system. And then when we look at the wind moving between the two, we see this kind of a movement. Okay, air moves from high to low at the surface, and that's how we get these rotations. Just back here, something to note: low pressure as the clouds, because when we have air rising, we have what's called unsettled air. We're bringing temperatures in different temperatures up from the surface, and that can cause storms. So what is this Coriolis effect I just mentioned? It is not why your toilet flushes and spins in a certain direction. That's because your toilet was designed to spin counterclockwise. Maybe you've heard rumors that if you go to the southern hemisphere, things rotate the other way. Well, so not their toilets. They just buy the same ones you buy. But yes, if we were to set up a proper bucket where water would drain out slowly through a tube, the water would eventually rotate counterclockwise in the northern hemisphere and clockwise in the southern hemisphere, for sure. But we're only worried about the northern hemisphere. So here's the top half of our globe, and we've got this little target right here in the Atlantic Ocean off the coast of South America. So if I want to hit this target, I have to aim over here because the Earth is rotating counterclockwise for the northern hemisphere aspect. So I can shoot over to here, but by the time my item lands, it's actually moving here. How that factors in is if I shoot at this target off the coast, I'm going to end up hitting that. The military uses this principle all the time. Maybe if you're into that, you know that sharpshooters and snipers actually have to take effect not only the curvature but also the rotation of the Earth. So the Coriolis effect definition is the apparent curvature of a path of an object as it moves over the Earth's surface due to Earth's rotation. And we're going to have a video on this as well, right? So look out for an Ed puzzle. All right, again, this just says if we were to fire a cannon at the equator from the North Pole, all right, the projectile would land to the right of its true path. What that means is everything in northern hemisphere rotates to the right. To the right, okay? It depends on where you're firing it from. Right? This gives us an apparent clockwise deflection. Note, we say apparent because things are not rotating. The Earth is moving under them. And you really need to know this only for the northern hemisphere. Don't worry about the southern hemisphere, although it does rotate the other direction in the southern hemisphere. But keep an eye out for some Ed puzzle videos about these concepts: weather instruments, pressure systems, and Coriolis. All right, everyone. I hope this video finds you well. Have a great time being home with your families, and hopefully we'll see you soon.